So in this video, dealing with review from your previous chemistry courses, I'm going to deal with a very important process, and that is a conversion to and from moles. And we can look at this from two different points of view. So let's have a look. So the first thing we're going to look at is a conversion from a mass to a number of moles. And in quantitative chemistry, it's really common. This is probably one of the most common things you'll do in chemistry when you're dealing with quantities of different chemicals. That's the conversion between mass and moles, or conversion of a number of moles to mass. And so we typically take the mass, which is given in grams, and we want to convert that to a number of moles. And we have symbols for this. You probably remember the symbol for mass. That's lowercase m, and hopefully remember the symbol for moles. That's lowercase n. And how do we do this? We need a molar mass. And again, hopefully you remember what the symbol for molar mass is, capital M. And so we're going to see in a minute how we use the molar mass to move between these two different variables. The other one that's pretty common, but really only from a point of view of doing analysis, unit analysis, and that sort of thing, is a conversion between a number of moles and a number of chemical entities. And so in this case, again, we're converting from moles and to entities. And I'll explain in a minute what the different chemical entities are. And so to do this, we use the Avogadro constant, and subscript capital A, the Avogadro constant. And you'll see in a minute, this is a huge number. Okay, so anyway, those are the two types of conversions I'm going to cover today in this small video, so why don't we get going on it. So first thing is to introduce you, to remind you of what's known as the mole hub. So the mole hub is a nice little schematic that allows you to move between the different things we've just described. That's move between a mass and a number of moles and chemical entities. So at the top of the mole hub is the number of moles, symbolized by N. So on the left-hand side here, we're going to look at the left-hand side first. What we want to do then is go from number of moles to mass, or vice versa, mass to the number of moles. And how do we do that? Well, what we need, as I mentioned, was the molar mass, capital N, molar mass in grams per mole of an atom. And we get this from, as I'm sure you remember, periodic table. So we look up the numbers on the periodic table. Okay, so that's one side of the mole hub. Mass to number of moles, we divide by molar mass. Number of moles to mass, we multiply by the molar mass. So the second side of the mole hub is this conversion from number of moles N down to, as I mentioned before, chemical entities. And so entities are the different sorts of small particles, very small particles, that we are familiar with in chemistry. And I would say that the only two that we can actually convert to directly are molecules and formula units. The other two we would have to convert to indirectly. And so how we do that is we use what's known as the Avogadro constant and subscript A. And so the Avogadro constant is a number that represents the number of entities in a single mole of a substance. That number happens to be 6.022 times 23rd entities per mole. That's what mole to the minus 1 means. So again, if we want to convert from moles to entities, we're going to multiply by this large number. Makes sense because we're always dealing with a humongous number of particles. And if we want to get from chemical entities back to number of moles, we divide by this very large number. So those are the processes we're going to look at now. So we'll do 3 quick questions, and this is the first one. What is the mass of 6.25 moles of calcium chloride? And so what do we need in this case? Well, we're going to determine the mass. That's what we're looking for. To determine mass based on the mole hub, we're going to need the molar mass of calcium chloride, and we're going to need the number of moles of calcium chloride. And we already have number of moles, 6.25 moles. And so how do we determine the molar mass of calcium chloride? Well, you can look in your periodic table, and you're going to add the mass of calcium and the mass of 2 times chlorine like you've done in the past, or if you're in a hurry, you can go to this website I've posted for you, molar mass calculator. This is from the University of Sydney. Just type in the formula, CaCl2, hit calculate, and there we have the mass of 1 mole of calcium chloride, 110.98 grams per mole. And so we will use that molar mass, 110.98 grams per mole. And so, as I said, we're looking for a mass of calcium chloride, and that equals the number of moles so we're looking for the mass of calcium chloride, and that equals the number of moles, 6.25 moles, times the molar mass of calcium chloride, 110.98 grams per mole. Moles divide it, and you're left with a mass of 694 grams. Don't forget sig figs, 3 sig figs in the answer, because in our question we have 3 sig figs. Okay, so that's the first thing, a simple calculation, number of moles to a mass. You should be able to go the other way as well, it's just as easy. Second question, 2.55 times 10 to the 22nd molecules of carbon tetrachloride. How many moles of this molecule would I have? So again, what do you need? Well, we're looking for number of moles, and what are we given? Well, we're given the number of molecules, and I often shorten molecules to molex, and so we have 2.55 times 10 to the 22nd molecules. And what else do we know? Well, we know the Avogadro constant, Na. So Na, and subscript A, as I mentioned before, 6.022 times 10 to the 23rd entities per mole, and so our entity in this case is molecules. And so number of moles of carbon tetrachloride, CCl4, equals number of molecules times 10 to the 22nd molecules divided by 6.022 times 10 to the 23rd molecules per mole. And so molecules divide out, you're left with 1 on 1 on mole, and so that equals 0.0423 moles carbon tetrachloride. That's 0. So that's the other side of the mole hub. Conversion from a number of molecules to a number of moles. You should be able to handle conversion of moles to molecules. So finally, let's put the two together. Here's the question. How many oxygen atoms are there in 0.065 grams of carbon tetrachloride? And so, again, if it helps, list what you need. Well, again, what are you looking for? Number of oxygen atoms. And notice this is oxygen atoms. That's not oxygen O2 because that's a molecule. So that's what we're looking for. So what do we need? Well, we're starting with a mass. So we have a mass, 0.065 grams of carbon dioxide, CO2. So we're going to need the molar mass of CO2. And the molar mass of CO2, if you were to determine it, no matter how you determine it, 44.01 grams per mole. But we're also going to need the Avogadro constant, Na, 6.022 times 10 to the 23rd entities per mole. And again, entities in this case, we're starting with molecules of CO2. So it's going to be molex CO2 per mole. And then we're going to have to use a conversion factor to get from molecules to atoms. So here we go. Number of atoms. We're going to do this in one step. Number of atoms equals mass divided by molar mass, 0.065 grams of CO2 divided by 44.01 grams per mole CO2. When we do that calculation, we are left with moles. We're going to multiply that by the Avogadro constant, 6.002 times 10 to the 23rd molecules per mole. When we do that, moles divide out and left with molecules. But that's molecules of CO2. We want an oxygen atom, so we have to multiply by 2 oxygen atoms per 1 molecule of CO2. And this is where molecules divide out. And so you're left with the unit of atom, oxygen atoms. And that's what we're after. And when you do the math on that one, you come up with 1.78 times 10 to the 21st oxygen atoms. So there you have it, the mole method, the mole hub, going from number of moles to a mass, from number of moles to a number of entities, or all throughout that mole hub. So you want to have a practice of those different types of calculations. They're pretty useful, certainly in the chemistry to come this year. And that concludes this video.